DC-DC converters with transformer isolation. It's a major topic area in switch mode power supplies, and we will be covering this topic in several videos. Now this particular video focuses on the need for transformer isolation and understanding some of the advantages, and we will cover this with a specific example of an application requiring a very large step-down conversion ratio. So first of all, what do we mean by this isolated DC-DC converter? So essentially we mean achieving galvanic isolation between different parts of the circuit through this high frequency electromagnetic transformer. So this transformer makes the different parts of the circuit electrically disconnected or isolated, but still maintains power transfer between these different parts through the electromagnetic induction in the transformer. So for example, this is a standard isolated converter. You may have seen this in previous videos as the flyback transformer. Okay. This high frequency transformer with its 3 windings divides the complete converter circuit into 3 isolated regions. So we have this primary region and the 2 secondary side regions, and clearly we can see that there is no electrical connection between the primary to either of the 2 secondaries or between the 2 secondaries themselves. Okay. But the power transfer is from the input side to each of these 2 load sides, the 2 secondary sides, and that is achieved through the electromagnetic induction in the transformer. Okay. Now if I were to draw the grounds on each side, each section, so this is the ground on the primary side, I would use a different symbol for this ground and a third ground here for the second load. So each of these 3 grounds are they are separate and they are completely electrically isolated. Okay, so the transformer, which is actually a fairly bulky component, it provides this electrical isolation in the power stage. But it is very important to make sure that we don't inadvertently lose this electrical isolation through the control stage. So most often we are interested in regulating the output voltage. Let's say VO2 is the main output voltage that needs to be precisely regulated. Then we would actually be sensing this voltage and then using the error between what we want and what is the actual voltage, process that error to control this MOSFET on the primary side. Okay. So it is very important to have some electrical isolation in this feedback loop as well. So here is the output voltage that is sensed using the sensor, and either before it is passed to the controller or from the controller to the gate drive or within the gate drive itself. In any of these 3 stages we should have some form of electrical isolation. Now that could be through an opto isolation in these signals, or it could also be high frequency based signal level high frequency transformer based isolation, again in the sensor or in the controller, or very often it is also realized in the gate drive itself using a pulse transformer for implementing this gate driver before it drives the gate of the MOSFET. Okay, so then why do we need the transformer isolation, or under what conditions would it be preferable to use an isolated topology in preference to a standard non-isolated converter? Okay. Now in many applications, a chief example is the medical application, and some other examples are a telecom application or even a computer power supply. So in these applications it is required by the user or maybe by the regulatory agencies like the UL. They require that the input in these applications is isolated from the output. It's galvanically or electrically isolated, and this may be due to for safety of the personnel or safety of the equipment, or in some conditions it may be to avoid ground loops in some of the sensitive loads. So regardless, the specifications require that you use an isolated converter. Okay. So for these applications, the designer has no choice but to use an isolated DC-DC converter. But there are situations where even if the specifications by the user does not demand a transformer isolation, we may still want to use an isolated topology. So one main example is when you have when the application requires a very large voltage conversion ratio, and that's one example that we're going to look at in detail in this video. So if you have this situation, a large voltage conversion ratio, then if you use an isolated topology, then that will result in a significantly better switch utilization. In the MOSFETs that you use, they will be better utilized. You may end up requiring a much smaller filter, mainly the filter inductor, compared to a non-isolated topology for the same specification. And very often these large voltage conversion applications would require that you use extreme values of duty ratios, either extremely small or extremely large duty ratios, and they become very difficult to implement, especially at high switching frequencies. Okay? So that is avoided by using an isolated topology, and all of these advantages lead to a higher power conversion efficiency and possibly higher power density. I say possibly because the transformer is a bulky component. So the savings in terms of smaller filters, the smaller losses, and therefore smaller heatsink, if that is more than the size of the transformer, then of course we have a higher power density. Another situation where we may want to use an isolated converter, even though it is not required by the specifications, is if we need multiple outputs. So this is again the flyback transformer example. So here I have two outputs, and they may be at completely different voltage levels, and they, in this case, they also are isolated from each other, okay, and from the input as well. So whenever you need multiple outputs, it is much easier to realize that using an isolated converter. Like in this example, all you need is add another winding and just one diode and one capacitor. You get another completely isolated output at a different voltage. Okay, so these are some of the main advantages. Now, what about the disadvantages of using a transformer? Now, first of all, a transformer is bulky, heavy component. So if you look at any SMPS, the transformer is probably the bulkiest component, and it's also relatively expensive. Okay? So if we can get away without using the transformer, then from the in the size weight point of view, it may be preferable to do that. But as we saw in the previous slides, there are some compelling reasons why we may want to use the transformer. So it's a trade-off between performance and the size and cost and so on. Okay. Now there are also some big disadvantage in using transformers. Chief among them is the parasitic components, the non-ideal components, namely the leakage inductance and the winding capacitance. Now the leakage inductance results in very large voltage spikes during the switchings, and the winding capacitance result in large current spikes. And also there is a energy associated with the leakage inductance, 1/2 Li squared, and the 1/2 CV squared energy in the winding capacitance. And these energies are dissipated each time there is a switching in the converter, unless we use a soft switching topology, which we'll be studying again in several videos. Okay? But in the absence of that, in hot switch converters, the losses in these two non-ideal components can be significant. Okay? So the losses, I mentioned the energy loss in the non-ideal components. In addition, you also have the core losses and the conduction losses in the windings of the transformer. And also, we have seen in previous videos that the size of the transformer would come down with the increase in switching frequency. But that relationship is strictly true only up to a certain switching frequency, maybe 250 kilohertz, in that range for the current state-of-art transformer cores. Beyond that, the size may not come down in direct proportion to the switching frequency, and the transformer may end up being a really big component there. So in spite of these disadvantages, let's see situations where it may still be preferable to use a transformer even though it is not required by specification. And as I mentioned, one key example is these applications which involve a large voltage conversion ratio, either step down in this example or even a step up. Okay. So my specifications are given here. The input is 200 volts DC and I want a 2 volts output DC. Peak current for the load is 10 amperes, so that results in VO times IO 2 times 10, that's 20 watts, and a switching frequency of 200 kilohertz. Okay. Now, so this specification can certainly be met using a simple buck converter. So after all, this is just a step down application, and by having a really low duty ratio, we can get a well regulated 2 volts output. Okay, so that is not a problem. But let's look at what are the disadvantages if we try to design a converter to meet these specifications by just this non-isolated buck. Okay. So the first disadvantage is really the total VA rating of the switch, okay, so which is defined as the product of the peak current rating of this MOSFET that times the peak voltage rating of the same MOSFET. Okay. So now in a buck converter, what is the for example, what is the voltage rating of the switch? Okay. So the voltage rating is determined when the switch is off, the diode is conducting, so this end is clamped to the ground. Therefore, the voltage across the switch is this entire Vn. Okay. So if the input is varying, then it is Vn max. But in our example, it is 200 volts. Okay. So the Vn here is 200. I'm sorry, the voltage rating is Vn, which is 200. What about the peak current? So the peak current is so the switch conducts the inductor current when it is on, and the inductor current, we know for a buck converter, is the average current is exactly same as the load current, which is 10 amperes. So even if you neglect the small high frequency ripple, the current through the inductance is 10 amperes. Okay? So that is this current. So this is really the switch current peak value, that's 10 amperes. Okay? So the product of these two, which is the total VA rating of the switch, is as high as 2000 with a unit of VA. And all this to realize just the 20 watts output. So you can clearly see that the switch is highly underutilized. We'll also see the same thing for the diode if you do the calculation. Okay. So the key point is, for this large step down ratio applications, if you use a non-isolated converter, then we end up using a very highly rated switch. Okay. And the next disadvantage is related to the switching losses in the MOSFET. Okay. Now I realize that you may not have seen a video on the switching losses described in detail. So I'm just going to give the equation for the switching losses for the MOSFET in this kind of a buck converter application, and go through the calculations and show that why it doesn't make sense to use a buck converter for this application purely from the switching loss point of view. Okay. So the equation for the switching loss, the total switching loss in the MOSFET. So remember that it is only the switching loss. In addition, you also have conduction losses in the MOSFET, which is not being considered here. Okay. Just the switching loss is which includes both the turn on and the turn off switching losses, is given by this expression, where this voltage is really the voltage of the MOSFET when it is undergoing a transition, which for a buck is simply the input voltage. And the current here is again the current in the switch when it is undergoing transition. And again, for the MOSFET of the buck converter, it is same as the inductor current, which is approximately equal to the load current. Okay. So that's Vn IO over 2 times the T on is the turn on switching transition interval, and T off is the turn off switching transition interval. And these are in the several tens of nanoseconds range for a good MOSFET. Okay. And Fs, of course, is the switching frequency, which is given in our specifications as 200 kilohertz. Okay. So if we substitute the numbers, Vn is 200, I0 is 10, so that's 2000 over 2, that is this 1000. And T on and T off both are assumed equal, and they are equal to 50 nanoseconds. So the sum of the two is 100 nanoseconds, that is this part, times the Fs, which is 200 kilohertz. Okay. So that works out to be 20 watts. Okay. So this is just one component of the entire losses, and that alone is equal to the entire load output power. Okay. So even if there are no losses, you will get an efficiency less than 50%. But there are many other losses, especially the conduction loss in the diode, conduction losses in the MOSFET itself, and this will eventually result in efficiency which is probably 30% or so, and that is certainly not acceptable for a switch mode power converter. Okay, so for these applications we would certainly need an isolated topology which would result in switching losses much less than this value. Okay, and the third disadvantage is related to the size of the filters, mainly the filter inductor. I believe you must have seen some of the videos on the buck converter analysis and the design, and we have developed the design equation for the output filter inductor. So if you know what is the peak to peak ripple delta I that you want to allow, then this is the equation for the L, and we have to use the worst case D, which is D minimum. Okay, so in this case the input is constant, so D is a fixed value, and that value is equal to the VO over Vin, that is 2 volts divided by 200 volts, so D of 0.01 in this case. Okay, so the L depends on 1 minus D, so with D negligibly small, it results in a very large value of the inductance. Since I did not have a value for delta I, am not really calculating the L, but you can clearly see that the low value of D results in extremely large value of the inductance. Okay. So that is one big disadvantage, and a related disadvantage is that the duty ratio is so small, in the order of 0.01. It also makes it difficult to implement this using standard PWM ICs, or if you're doing a digital implementation, it's even more difficult. Especially at frequencies in the order of 200 kilohertz and above. 0.01 times 0.01 times 1 over 200,000, that will work out to be a very small on time, and that becomes difficult to implement with current PWM ICs. So if you for the same specification, 200 volts input to 2 volts output, instead of a standard buck converter, if we used, I would probably use a forward converter. It's one of the isolated topologies that we'll be studying in detail, a forward converter instead of a buck. If you use that isolated topology, then each of the 3 disadvantages that I talked about, namely high values of switch VA rating, high switching losses, and the high inductor size requirement, each of these would be significantly reduced if you use an isolated topology, and that would lead to better efficiency in spite of the losses, extra losses in the transformer. You would still end up having a better overall system efficiency, and most often a better power density, more compact size, in spite of the bulky transformer. And that is mainly because of the reduction in the filter inductor, as well as reduction in the heat sinks because of the lower losses and better efficiency. Okay, another completely different example where you are better off using isolated topology, isolated DC-DC converter actually. Even though it is strictly by code, it may not be required to use isolation. Okay? And that example is a photovoltaic solar PV microinverter. Okay? So this is the configuration. So each PV module, like rated for 200-250 watts power, they give a DC output in the range of 30 volts to 40 volts, depending on the operating conditions. Okay? Now these are, so a microinverter is something that is mounted directly at the back of these PV panels, and they provide directly an AC output connected directly to the grid. Okay. So this is the configuration. There are multiple panels, and each panel has these microinverter which provide AC, and that is connected directly to the grid, out to the AC bus. Okay. So the microinverters have typically 2 stages: a DC-DC converter, which steps up the 30 to 40 volts DC voltage from the PV panel to about a 400 volts regulated DC voltage, and from that you do a sine PWM to convert that to a 240 volts RMS AC sinusoidal voltage. Okay. So now we are looking at the application of this DC-DC stage, 30 volts to about 400 volts DC. Now many utilities still demand that there is a transformer here, but the newer codes, the NEC codes, they do allow transformer-less PV inverter topology. So it is allowed. Okay. But what I'm trying to say is, even though it is allowed to not have a transformer, For this applications, it may be preferable to use the transformer because of the large step-up conversion ratio. So you may be able to implement this by multiple stages of a boost converter, but using an isolated converter would result in better efficiency, better power density compared to a non-isolated solution.